All right, response. Yeah, what's the response, right? Yeah, because the terminology in our engineering environment, we know, excuse me, input means the driving force, right? Then response, that's the output. So output is the solution. Yeah. Then RC circuit, R resistor, C capacitor. Yeah. And we don't have L. So here you can see in this system, we don't have the L part. So that is the, so that, look at the graph. So you have R component, C component. Yeah. But a V, so V, the voltage, this V is a special function. Yeah. So it is, the function is like this. It's called single rectangle wave. Yeah. It's a rectangle wave. Single rectangle wave. Yeah. So how to solve this application problem? Yeah. Find the current, little I of t. Yeah. In the RC circuit in the figure, if a single rectangle wave with voltage V0, yeah, so the value is V0, but that value only used between A and B interval. Yeah. Outside this interval, it's 0. Yeah. So we need to, first we need to represent this function. To represent this function, we use U function, subtraction of two U function with different shifts. Yeah. The first one, starting from A, so T minus A, so you start from A. The second, you start from B, then you do subtraction, right? Because if you don't do subtraction, both functions have same value V0 after B. But after subtraction, this part is gone, okay? Cancel out. After the cancellation, so only between A and B, its value is capital V0. Yeah. All right, so that's the representation. Yeah. Okay. Yeah. Now we can set up equation. Yeah. Yeah. R part, C part, R times little I of t. Yeah. We can use little I. Okay. Yeah. Yeah. So you may want, some of you, because before we use capital I to represent current, right? Yeah. But here, why people like to change from capital I to little I? Yeah. So this little I function, the current function, so you should not confuse with the complex symbol I. Yeah, it's different. So the little I. The reason is simple, because here let me explain why people change our usual capital I function to little I function. Yeah. The reason, because we will use the Laplace transform, right? Yeah. The reason is related to the Laplace transform. Yeah. Because Laplace transform, remember, Laplace transform of little y equals capital Y, right? Yeah, equals capital Y. And, so here you can see the Laplace transform of the little some symbol function equals capital F. Yeah. Then, in order to use Laplace transform because the capital symbol represent the Laplace transform of that function. Then its corresponding original function, we need to use the lowercase. So here we want to use the capital I of S to represent the Laplace transform of the little I function. Okay? Yeah. I of t. Yeah, because here, in order to separate from the complex symbol I, so we use little I of t. Yeah. That's the reason people use the little I. Okay? Yeah. All right. Yeah. Then here you can see the original capital Q becomes little q of t. Yeah. Yeah. Before we use capital Q to represent the electric charge, the total electric charge. Yep. But here we need to use capital Q to represent the Laplace transform of this function. So we have to use little q to represent the electric charge of that in that capacitor C. Yeah. All right. So now this is our first equation. Yeah. Then after that, we need to apply Laplace transform both sides. Yeah. Okay. Yeah. Yeah. So let's do one by one. Yeah. All right. Yeah. If you write explicitly, yeah, before we apply, so we write, second term and the right-hand side explicitly. Yeah. Because the Q, electric charge, that is the integral of the current function. Yeah. Okay? Yeah. Based on the, formula. Yeah, basic formula. Yeah. So now we need to work on this formula. So when we apply Laplace transform, we should apply it on this second equation. Yeah. All right. So let's do term by term. Let's apply Laplace transform term by term. Okay. All right. Yeah. So let me copy some related formulas below. Yeah. The shift. Yeah. Because here you have U shift version. So we need to use this formula, right hand side. Then now Laplace transform of the first term, yeah, R constant, little I. Now, after we apply Laplace transform, it becomes capital I of S. Yeah. Then, how about the second term? We apply Laplace transform. Remember, we have that integral, Laplace transform of the integral formula. Yeah. 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 So here I didn't copy, but because I can write it, easily. Let's recall. We have this formula. Yeah. Yeah. Let me write it. Inside it's an integral. Okay. 0 t f of tau or equals over S, right? Yeah, divided by S. Okay, divided by S. Okay, yeah. So now, if you apply this formula, yeah, so inside the integral, it's a little I function. Yeah, little I function, then capital I and divided by S. Okay, C is constant. Yeah. So that's the Laplace transform of the second term. Yeah. The left-hand side, the straightforward, yeah, capital V0 constant, you factor it out. Then remaining two terms, yeah, the first term, use the first function. Second term, the second function. Just change to b. Yeah. 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 So that is, so you get a algebraic equation. This is algebraic equation. Okay? Yeah. You can solve it for I function, I of s. So you can write I of s equals this algebraic equation. Yeah. Capital V0, capital C, capital R, little a, little b, they are all constant. Only s is the variable. Now you need to take the inverse Laplace transform. Yeah. Inverse, yeah. So you write it in this form. Yeah. So here we, yeah, hope you can see the division. Okay, yeah. So divided by, yeah, so what's that? Yeah. So you, both numerator, denominator, you do division by RC. Yeah, RC. Yeah, because you want to make the coefficient of s after division becomes 1. S plus a constant number. Okay? Yeah. Numerator also a constant number. Yeah. Yeah. Because in that way you can treat as s plus constant, it's a shift, right? S plus something, it's a shift operation. Yeah. So you need to apply that shift theorem. Yeah. It's our first shifting theorem. All right? Yeah. 1 over s. Yeah. First you need to, what is the inverse Laplace transform of 1 over s? Yeah. It's 1. Yeah. Yeah. So here you can see yeah, in order to calculate inverse Laplace transform, I make this whole thing. I use the capital F to represent that whole fraction. Yeah. Yeah. Now, because now we want to find the inverse Laplace transform of that capital F. All right, yeah. And we need to use this simple formula. Okay? Yeah. Inverse Laplace of 1 over s equals 1. Okay? Yeah, that's simple. It's 1. Okay? Then shift, then you need to do shift. Shift, you multiply that e something, right? Yeah. All right. Yeah. Now you do shift by, so s minus a, so you need to multiply e to the a t. Yeah. So what's that a? Yeah. A equals negative this number, okay? Yeah. 1 over RC, this number is negative a. This number equals negative a, okay, because of s minus a. Here we have plus. Yeah. Yeah, so that number is negative a. Yeah. All right. Then, yeah, so here, let me erase this. All right. Then we need to use the second shifting theorem. This is the second shifting theorem. Okay? Yeah. Yeah, here, because you look at this, e to the negative as times capital S, capital Fs times e inverse, so you should have this term, yeah, because you need to calculate the inverse. Yeah. All right. So, but there are two terms you need to calculate. Yeah. All right. Yeah. So the next slide, I want to do the calculation. Yeah. The final round of calculation. Yeah. All right. Yeah. First, we calculate the capital F part. Yeah. Because the remaining, we apply second shifting theorem. Okay? Yeah. First, let's calculate the inverse Laplace transform of f of s. All right. Then, the constant part can be factored out. Yeah. This constant part, factor out. Yeah. So inside, this is the a part, minus a, right? So minus a. A is that negative, that number. All right. So then, e, yeah, so here we use this function, e to the at, because a is negative 1 over RC. And little f is 1, yeah, because when we use this function, little f is this 1. So this number times 1. Yeah. Yeah. So this is little ft. Okay? Yeah. Little ft. Because inverse Laplace transform of capital F. So we use notation little f of t. Then we need to apply the second shifting theorem here. Okay? We can apply. So little I of t inverse, the inverse we split into two terms. Yeah. The first term we apply the second shifting theorem with A, yeah. Then B, so A, little f of t, yeah. So that copy, that second term, B version, yeah. Shift by B units. Yeah. Then little f of t, we know this is little f of t. So we need to write, do substitution, little f of t. So constant out inside, so that little f of t and the u shift, and another little f of t with shift by b units to the right. So you get that expression. See? Yeah. Yeah. Hope you can follow the calculation details here. Yeah. Yeah. So the manipulation, you can see, you need to do a lot of shift operation. Okay? Here you have two shifting theorems. First and second shifting theorems. Yeah. Yeah. All right. So then, you need to, first you need to understand the structure in the right way. Yeah. The structure in the right way. Yeah. Yeah. So then you calculate Laplace, inverse Laplace before the shifting operation. Yeah. After that, then you apply the, right shifting theorem to get a final answer. Yeah. Try to get used to this kind of calculation. Yeah. Yeah. So you need to practice. You need to get experience. Yeah. Yeah. All right. Yeah. So if you can handle those basic formulas, yeah. So here you can see, first you need to familiar with those basic formulas. Yeah. After that, you need to be familiar with two shifting theorems. Two shifting theorems. All right? Then you also need to be familiar with the derivative formula of the Laplace transform and the integral formula of the Laplace transform. Okay. Yeah. So that's all you need, yeah, to solve equations, yeah, with, yeah, these basic terms. Yeah. All right, so so we complete this application problem, and we complete part A of Module 3. Next, we need to jump to part B of Module 3. Yeah. So we can get started. Yeah. So we can do 2 topics. Yeah. All right, so let me get out to, yeah. Then part B. Yeah. All right, part B. Yeah. The title, also 2 parts. Yeah, the title, Conversion to Systems of ODEs, the first part. The second part, Laplace transform of Dirac's function. Yeah, Dirac function closely related to the Heaviside function. Yeah. But there is another special function. It is very important in engineering application problems. Yeah. All right. Yeah. the first topic, B.1, conversion of an nth order ODE to a system of ODE. Yeah. All right. Here we use a different view on nth order ODEs. Yeah. Yeah. So we start with a general ODE form of nth order ODE. Yeah. All right. Yeah. Then we take a different view. Yeah. Because so why you want to take a different view? Yeah. So the reason we know usually we know when the order of the ODE is too high, then it becomes harder and harder to solve, right? Yeah, because the order, if the order is pretty high, so then, the solution will be harder. Yeah. So here we want to, use a special view to make the order lower. Yeah. If we can make the order lower, then we feel more comfortable. Yeah. All right. The approach. Yeah. If we can convert an nth order ODE to a linear system ODE, then we can apply many tools in linear algebra to solve the higher order ODEs. Yeah. We know linear algebra has a lot of powerful tools. Yeah. Eigenvalue, remember eigenvalue, a lot of matrix related techniques we can apply to solve the higher order ODEs. Yeah. So that's a good view to take. Yeah. All right. How to understand? Yeah. Yeah. So the high order ODEs. Yeah. All right. Yeah. Here we assume this y of x is the solution function. Yeah. With one variable, x as the variable. Yeah. Then for this general form ODE, can we introduce some new variables to represent these derivatives, right? Yeah, new variables. Yeah, yeah. All right, so that's the idea. Yeah. All right. So we treat, so here, because this capital F function, when we write this way, we treat each y expression as a variable. Okay, so f is the first variable, then y second variable, y prime takes the position of the third variable, and so on. All right? Yeah. So here, can we introduce new variables to represent these symbols? Yeah. So we treat them as independent variables. Yeah. Although we know they are correlated, right? Yeah. So some students, you may feel, so y prime and y are correlated, and the y double prime and the y prime also correlated. Yeah. So you may argue they are correlated, not completely independent, right? Yeah. But first, let us use independent variables to represent these notations. Yeah. After that, then we address their correlations. Yeah. How about that? Yeah. So, all right. Yeah. So now, let us do that. Yeah. Yeah. So it's hard. So, yeah. In that way, the immediate result will be the order of the ODE will be much smaller. Yeah. So we add new variables. Yeah. That's our cost, right? Extra cost. We add new variables. But after we pay this extra cost, the benefit of this way we bring down the order of the ODEs. That's the benefit. Yeah. All right. Yeah. Yeah. So here, we will do that. Yeah. So we will use more functions. Yeah. So the new variable, each new variable represents a new function. Yeah. So we will use new functions to reduce the order of the derivatives. Yeah. That view. Yeah, that view. Okay? Yeah, so let's do it here in this slide. Yeah. All right. Go convert higher order derivatives to first order derivatives with more functions. Yeah. Yeah, because, so here, nothing is free, right? So when you solve difficult problems, yeah, so, nothing is free. So here, because you make the higher order ODE to first order ODE, but you have to pay somewhere else. Because you cannot get it free, right? You cannot get this nice property free. Yeah, this is nice property. First order derivatives, nice property, free. You have to pay in some other forms. Yeah. This is the form you pay, okay? So, because you use more functions. Yeah. The more functions, so that means more cost. So the cost is high, okay? You need to pay more. Yeah. Yeah. More functions. Yeah. All right? Yeah. Yeah. Trade-off between orders of derivatives and the number of functions. Yeah. Trade-off. Yeah. So you bring down the orders, but you raise the number of functions. Okay? Yeah. Yeah. So that's fair. Yeah. All right. Straightforward conversion. Now we are ready to do the conversion. The conversion is very simple. Yeah. Straightforward. Yeah. All right. Y will replace original y function by a new function we call the y1. Yeah. Okay? y1. What subscript 1? Yeah. So y prime we replace it by y2 subscript 2. Yeah. And so on. Okay? Yeah. So y to the y n minus 1 derivative. Right? N minus 1 order derivative. Yeah. So there, yn. Okay? Symbol. Yeah. All right. And the last one we do not need, right? Yeah, because there is the last one. Y nth order derivative. Yeah. Nth order, yeah. So you may ask, why we do not need to use a new symbol to represent nth order? Because this equals yn prime, the first order derivative of yn function. Yeah, because our goal, we are allowed to use the first order derivatives, right? If we can use first order derivative, why we need to introduce a new symbol for nth order derivative? We don't need. Yeah. So we can save one symbol, right? Yeah. All right. After this kind of simple mapping or simple substitutions, yeah. Yeah. All right. Yeah. We can write, yeah. So here, the equation, yeah. Yeah. So here, actually, we changed the, you can see, we changed the original equation, right? So here, yeah, let's say, yeah, this equation we want to consider. Yeah. Yeah. Because I may like to go back to the previous slides, yeah, to see, to compare. All right. Yeah. Oh, yeah, see? Yeah. Look at this general form. It's different from it. Yeah, so look at the general form. It's different from the one we consider here, right? Yeah. All right? Because that general form, Still too hard. Okay, so that form is too general. Too general, that means it is still too hard. So what we can do, what we can do on a simpler form. So this is a simpler form. Simpler than that general form. Okay, the general form still too hard. Yeah. So here we consider a simpler version of the general form. Yeah, that means we can find y nth order derivative. Yeah. Nth order derivative of y. Okay. Yeah. Then, now because we have new variables, so this big equation we can write as y n prime equals, this time we use all the new variables. Then the relationship, because these functions, they are not completely independent, right? They're a relationship. The relationship is simple. Okay? Yeah. So y1 prime equals y2. y2 prime equals y3, and so on. Because in this way, you can see, in this way, so you may feel, what's the benefit, right? What's the benefit? So here, what's the benefit? So then the benefit is because if this f function is still important. If this f function is a linear function, then we get a linear system, right? But f function is not a linear function, then still hard, still too hard, because it's a non-linear system. It's a non-linear system, still very hard to solve. All right. So next, so I think later, before I jump to the next new topic, let me say something before we get to the new topic. All right. So first we know in the general ODEs, most of the ODEs we cannot solve. Okay, so our current mathematical tools still too limited, not powerful enough. So we can. So the most actually, if we consider all the possible ODEs, most of the ODEs we cannot solve. What we can do so far, we can only solve relatively small number of special types of ODE. So here, the we means, the whole mankind, okay, not just us, okay? The whole world, we cannot solve, okay? Because too hard. Our mathematical tools still not powerful enough. And because in the real world situation, even if you cannot solve, you cannot find the solutions, but in the real, you have to solve the problems. Many important real world problems. So if you do not know how to apply mathematical tools to solve, you cannot give up, right? So you have to find the solutions that I mentioned before. In that situation, we will use the numerical solution to approximate the real solution. What I say we cannot solve, that means we cannot find mathematical formulas for the solution. That's the meaning. We cannot find the mathematical formulas. Too complicated. So we don't know how to solve. All right, so that kind of thing. But you don't need the mathematical formulas to represent the solution, right? You can use numerical values to represent the solutions, right? So then, when we use numerical solutions, then we, the real world problems, then we can approximate. Okay, so we can get a very good approximation to the real world problems. Yeah. All right. Yeah. So after the midterm, I try to use 1 or 2 classes to introduce the numerical methods. Yeah. Just give you some ideas. Yeah. Although we do not have a lot of time to learn the numerical methods, yeah, but at least I show you some examples to let you feel about how to use the numerical methods to approximate solutions of the ODEs. Yeah. ODEs or even PDEs. Yeah. So ODEs and the PDEs. Yeah. Yeah. Probably I try to use 2 classes. One for ODE, one for PDE. Yeah. All right. Yeah. All right. So that's some comments. Then another one is then later we need to focus on the linear F. Yeah. Because that's the type we can solve. Linear F. Nonlinear we cannot. Okay. Nonlinear we have to use the numerical solutions, approximations. Yeah. Yeah. But for the linear, we have a linear system. Yeah. Then we can use linear algebra tools to solve the linear systems. Yeah. So that topic I want to leave after midterm, module 4. Yeah. Module 4, I want to cover linear systems. And series solutions. I want to put the series solutions and the linear system together in module 4. Yeah. After midterm. Yeah. So this module 3, we will not solve linear system. Yeah. So, all right. Next, B.2, Dirac's delta function. Yeah. Here I only have less than 10 minutes. Yeah. Let me just talk about this Dirac function a little bit. Yeah. Yeah. So next time we will calculate the Laplace transform and other related formulas. Yeah. Yeah. All right. Definition of Dirac's delta function. Yeah. We need to define this function. Yeah. Yeah. Its definition actually, very special. So it's not like our usual definition. Yeah. So we know definition of the Heaviside function, very simple, right? Yeah. But definition of this Dirac's function, much harder than that of the Heaviside function. So let me show you. Yeah. Definition. Before we define that Dirac function, so we need to define some intermediate function. Okay? Yeah? Yeah. So here we introduce the function special sequence of function. So the function with the subscript k, defined as, so here you can see it's a step function. Yeah, it's a step function. Yeah, with value, non-zero 0. So non-zero 1 over k, then other than that 0, but non-zero value in this interval. Okay, between a and a plus k. Yeah, that otherwise 0. Yeah, that special function. Okay, for all the positive integer k's, k equals 1, 2, 3, 4, 5. Positive integer k's. Then you can, if we draw the graph, you can see f sub k, this, bar, rectangular bar. Yeah, yeah. It has a special property. The area of this rectangle is 1, always 1. Okay, and when you change k, it's always 1. Yeah. Oh, just a minute. This k not necessary integer. Yes, so I need to change. Yeah, because At the beginning, you can use integers, but later, we want to make this k non-integer, and this k becomes smaller and smaller. Yeah, yeah, because you can see the graph, this rectangle, very skinny. Yeah, because you will make this k smaller and smaller, then this rectangle is more and more skinny. Okay. Yeah. We want that kind of shape. Yeah, that kind of shape. Yeah. All right. So eventually we want to make a k goes to 0. Yeah. So that's why it's not integer. Okay? Yeah. So at the beginning it's not important. Okay? When k is large, then it's those fk not important. What are those important k? So when k very small, f sub k function, when k very small, those functions are important. When k is large, it's not important. Okay? Yeah. Yeah. So here you need to consider this special fk function. Yeah. All right. Then the delta function, we use the limit way. Yeah. We define delta function of t minus a as the limit when k goes to 0, f sub k of t minus a. That's the delta function. Yeah. But here there is a question. Does the limit exist or not? Because the limit may not exist. Think about that. Yeah. When we use the limit, how do you know the limit exists? It's possible the limit does not exist. That's the hard part. Okay? So that's the hard part. So there is a, big question mark here. That is existence of this limit. It's a big question mark. All right? Yeah. Yeah. Actually, it does not exist. Okay? Yeah. Yeah. Because based on the limit definition, we know the limit definition, right? Based on the limit definition, this limit of all these functions does not exist. Yeah. But why you still use this notation? If it does not exist, how can you define the delta function, right? How can you define the delta function? Yeah. Based on the limit, based on the definition of the limit, delta, yeah, so this delta function. Yeah. So it's not a function, okay? It is not a valid function in math. Yeah, we know. Function, there is a definition of the function, right? Yeah. So it does not, this delta function does not follow the definition of the function. All right? Yeah. Yeah. But why people use this special thing, special notation? Yeah. Yeah. So here, yeah. So this question, yeah, because this notation is very useful. Yeah. Although it looks like it's not rigorous. It is not a rigorous math here, right? Yeah, so that's why a lot of mathematicians, before, so they had problems, yeah. But this special here, let me just temporarily call it a function, okay? This special function is extremely useful in real-world applications. Yeah? Yeah. So that's why people have to accept the special object. Yeah. So let's treat it as a special object. Yeah. It may not be a function. It is a special object. Yeah. All right? Yeah. So there. All right. Yeah. Because very important in engineering. yeah, in solving engineering problems. This tool, we can treat it as a tool. Okay, this tool is very powerful in solving many application engineering problems. So we need this tool. Okay, yeah, all right, yeah. So here we give name, so Dirac delta function or unit impulse function. Yeah. Because in many engineering problems, people need to model the impulse phenomenon, right? Yeah, so a lot of things has that impulse property, impulse phenomenon. You need to model it. What's the appropriate mathematical function you can use to model the impulse phenomenon, right? Yeah, so this Dirac delta function is the best way to model it. Okay, all right. So here, yeah, conclusion. Yeah, so let me finish in 1 minute. The conclusion, this delta notation, it is not a valid mathematical function. Yeah. Then people call it generalized function. Okay, so it's not a legitimate, legal math function, but people just call it generalized function. We agree it's not a function. Yeah. But how about we call it generalized function, right? Yeah. Because we generalize in certain way. Yeah. Yeah. Generalized. So we give it a vague description. This generalized function, some vague description. All right, let me stop right here. So next time, let's continue to understand the special object, yeah, special generalized function. Yeah. All right, that's it.